Hi there everybody, welcome to the next lecture in the Chem Complete series for aldehydes and ketones. So last time we talked about how to name aldehydes and ketones, and now we are going to start taking a look at how to form these functional groups before we start to study the reactions that they undergo. So this lecture is going to take a look at how to form aldehyde functional groups. And there's three primary ways that we can deal with that, and that's coming up on the channel right now. Okay, so depending on what you may or may not have already studied, some of this is potentially going to be review for you. Specifically, aldehydes and ketones are usually taught after alcohols. And so if you've gone through the alcohol chapter, you've been exposed to oxidation and reduction reactions, and you have some familiarity with that process. So I am going to recap some of these reactions that you may have come across already, but there is one that you probably haven't seen yet unless you've gone and you've studied the upper level carboxylic acid derivatives, particularly esters. So we'll take a look at that reaction in a minute here. Okay, but the first one that we want to talk about is the use of selective weak oxidation of a primary alcohol. Now there's two important parts here that I want to mention. A weak oxidation, which is why we're saying selective, because if it's not a selective oxidation, the primary alcohol, which is the other important point here, is going to be oxidized all the way up to a carboxylic acid functional group instead of giving you an aldehyde. So basically you need to be able to stop the oxidation process partway through, and we do that by using a weaker reagent when we try to oxidize the primary alcohol. So for instance, let's go ahead and use propanol as our example. So if I have a propanol and I would like to have it undergo a selective oxidation into an aldehyde, the reagent that I would use is going to be PCC, and that stands for pyridinium chlorochromate. Okay, it's like a pyridine salt with a chlorine chromate that is attached, and that is a weaker oxidizing reagent. So PCC is the oxidizer of choice. In some of the newer textbooks, you may see Des Martin's reagent. That's one that I personally used in graduate school. It has the same sort of effect as PCC does. And so as long as you've got a selective weak oxidizer, you should be able to complete this. Many times you may see CH2Cl2, which is just dichloromethane. That's a solvent that you're running this oxidation process in, not a direct part of the reaction itself. Okay, so what you get as a result here is you still keep the carbons that are there, but that carbon that has the alcohol attached to it towards the end, the terminal carbon there with the alcohol on it, that's the carbon that gets oxidized up into the aldehyde, right? So it's important that while we're doing this, you count, and we've got 1, 2, 3 carbons here. Always double check your product. You should have 1, 2, 3 carbons here, right? That third carbon turns this entire chunk or piece into the aldehyde group that we see over there. Okay, so that is the first of the three methods for creating aldehydes, is to use a weak oxidizing agent on a primary alcohol. And it has to be a primary alcohol because if it's a secondary alcohol, it'll give you a ketone, which we'll talk about in our next lecture, forming ketones. And if it's a tertiary alcohols do not undergo oxidation because they would give or attempt to result in some sort of a carbon that has more than 4 bonds, right? You'd have a 5-bonded carbon, and that breaks valency rules as far as Lewis structures and what carbon is capable of with its hybridization process. Okay, so number 2, we want to use the selective reduction of an ester. Now this is the one that I was mentioning a minute ago that might be new to some people if you haven't gone through and looked at the carboxylic acids and their derivatives chapter, which is typically taught after aldehyde and ketone material. So when we get ready to do this, I'm going to put a generic ester up here. And this is going to be the opposite of what we just saw. So this is going to be a reduction process instead of an oxidation process. And when we deal with a reduction, that means that we're going to be taking the carbonyl group and bringing it down to a lower oxidized state. So typically when this type of behavior, this type of reaction is first taught, it's taught in the context of alcohols. But we can take an ester and we can partly or weakly reduce it down halfway so that we don't get an alcohol from the ester, but instead we stop at an aldehyde. It's almost the exact reverse of what we just talked about with the weak oxidation. It's a weak reduction of an ester. So the ester group that we'll go ahead and use is just a simple one. Let's put an ethyl group here. And then we'll go ahead and make it a methyl ester here. Okay. So something that looks like this. So simple ester, keeping in mind that ester is really R, C double bond O, O, and then another R group, right? That's the functionality of an ester. Okay, so the reagent that we use here is abbreviated, kind of how PCC is, and it is called DIBAH. D-I-B-A-H. And what DIBAH is diisobutyl aluminum hydride. So you know lithium aluminum hydride, which is a very strong reducing agent. This is kind of one that is slightly nerfed or weakened, and we call it DIBAH. It's diisobutyl aluminum hydride, right? So what we end up with, this reagent itself, which I'm going to draw out down here, just so you could take a look at it, okay, would look like this. Then you've got the CH2. So there's your isobutyl. Okay, that's going to be coordinated with the aluminum that'll be in charge of generating a hydride, and then it's diisobutyl. So you've got another one on the other side, just like this. Kind of a bulky reagent that we're looking at here, but this is your DIBAH reagent. Okay, and so what it does is it is going to generate hydrides. That's what the H is standing for. Okay, H minus, and it is going to do so in a weaker fashion. It's not going to be as aggressive in the hydride generation and application as the lithium aluminum hydride would be. Okay, now the important part that we want to focus on here is the result. And so what we get is we're going to cleave off that right-hand portion of the ester with the oxygen, but we are going to maintain the C double bond O with hydrogen, right? So if I used lithium aluminum hydride here, it would have taken it down to the respective primary alcohol. I would have gotten propanol out of this. But because I used DIBAH instead, I ended up with the aldehyde version. I didn't reduce it all the way down to the alcohol. And one other thing I want to note here, you're going to see this written very often. It is run at cold temperatures. So most typically you're going to see minus 78 degrees Celsius. The reason for that is that is the temperature that you usually get when you use acetone and dry ice. So if you mix those two, you can create what's called an acetone dry ice bath, and that is the approximate temperature. It's minus 78 degrees Celsius. And this also helps to slow down the reduction process. You use a slightly weaker reagent, and then you make it weaker or slower still by lowering the thermal energy that's around, because that's going to play around or affect with the kinetics. It's temperature dependent. And so as we slow things down at a molecular level with a cooler temperature, the reduction doesn't occur nearly as readily as if we're doing it at room temperature, and certainly at elevated temperatures. Okay, so this is a way that you can get aldehydes. You can take an ester and then you can reduce it selectively down to the respective aldehyde. Okay, and the last one that we're going to wrap up with here is another one that you may have come across, because this is going to involve alkenes, which are carbon-carbon double bonds, and that's usually taught at the beginning of the first half of the semester for organic chemistry, whereas aldehydes and ketones is most definitely usually taught in the second semester of organic chemistry. So you may have seen this at some point, but this reaction is not one of the ones that's focused on quite as much as some of the others, like the BR2 edition and stuff like that for alkenes. So it's a good thing to bring up and remind students about. Okay, so the alkene that you can have here could be, any sort of substituted alkene, but I'm going to give a specific example because I want to show you something here. And again, this can also create ketones, so we're going to be bringing this back up in the lecture we have after this one. Okay. So I want to go ahead and I'm going to make this my alkene here. Okay, and I'll make a hydrogen here. So what you can do if you have an alkene is you can subject it to, number one, ozone. So this is commonly referred to as ozonalysis. It's also known as oxidative cleavage, which is the name that we have up here. Okay, and then in step 2, you're usually going to expose it to zinc metal and some form of H+. So a lot of times you'll see HCl, you'll see H3O+, but some sort of acid with the zinc is required in the second step for the proper oxidative cleavage to occur and finish. Okay, now what you get, the easiest way that I teach students this is that you come and you directly cleave or chop the bond in two, and right where you see that drop or that cleave, you're going to separate the two parts out and give an oxygen while maintaining the double bond. So what does that mean? It means, okay, the left-hand side has a CH3. It's got that C. Now that C had a double bond, and then it has an H, right? So if you're confused at what I'm looking at here, I'm looking at this right here, but I'm maintaining the double bond that's there. And in place of it, instead of having the carbon on this other side here, we're just going to put an oxygen here. And that is the oxidative cleavage that has occurred. Okay, so plus, because I've got another product over here, I'm going to do the same thing. I would also have, let's go top to bottom, the methyl. I would have the double bond where I'm going to put the oxygen. And then I would have the ethyl group. Okay. So if you take a look here, this is an aldehyde. Now the other one is a ketone. Okay, so if this hydrogen had been an R group instead, like a methyl or a propyl or something of that nature, all I would have gotten is ketones out of this. And likewise, let's say that this wasn't a methyl and instead this was a hydrogen. Well, then I only would have gotten aldehydes out of this. Okay, so sometimes this process will give you only ketones, sometimes it'll give you only aldehydes, and sometimes it can give you ketones and aldehydes. Sometimes if the alkene is symmetrical, it'll give you two of the same aldehyde or ketone. Okay, so you can go back and you can review this material from previous chapters and lectures that we have on the channel. But I just wanted to bring this up. This is another way that you can make aldehydes. Okay, it's usually one that isn't spoken of as much just because DIBAH and oxidation of a primary is going to be more readily used in literature, in actual synthetic techniques. Not to diminish this, but those two are much more common, so you're going to come across them more often. Okay, but this is around, and this is a legitimate way to make aldehydes. So that is going to be it. We're going to wrap up here. I encourage everybody to head on over to chemcomplete.com. We have lots of free resources over there. We also have guides if you feel stuck on a specific topic or subject, including things like NMR spectroscopy. Go over and check it out. Even if it's just for the free resources, it helps to support the channel. It drives traffic over there. Like, subscribe, comment, all that YouTube stuff that's great. Okay, but the best thing that you can do to continue supporting us is just watch the content right here on the channel. That's all the support that we need. But if you want to support us further, head on over to that website. All right, everybody. I will see you guys for the next lecture, Forming Ketones.